first thing for notation, I denote by SGN, capital SGN, the set-valued SGN function as usual. And, well, I denote by UPR, that one, that means the subdifferential of the indicator function of R plus. I think this one has a name. Everybody uses it, but I think this one is much more important than that one. So I think it should also have a name, and this is why I invented the UPR, which means unilateral primitive. Because I really don't like that this one has a name and that one not. So whenever you see the UPR, I mean here that function, so that it's a subdifferential of the indicator of R plus. Now, there are basically two approaches to analogies between electricity and mechanics. The first one is the charge approach, and the second one the flux approach. I have chosen the charge approach, and within the charge approach, positions in mechanics correspond to charges in electricity, velocity in mechanics to current, because it's moving, so you can think about something which is flowing. And due to that, in kinetics, we have, in mechanics, we have forces, and the associated thing in electricity are voltages. And I also allow for impulsive forces and, as a consequence, for impulsive voltages. If I have both of them, then I collect it in the associated measure and write it that way. So if you see a calligraphic character, that means always that it consists of a Lebesgue part and an atomic part. Now, here in that table, you see the classical elements. We have here mechanics, and in this column, electronics. Inertia, mechanics are masses, and if you choose the charge approach, then in electronics, you have inductivity for the inertia. The dissipative element in mechanics is the damper, and in electronics, the resistance. Energy storage in mechanics, springs, and in electricity, capacitors. So this is classical, yeah? And you see that I write this one already as a measure because I do not want impacts to be excluded. So I definitely allow for impacts and velocity jumps, and the same here. Now, non-smooth elements. So in mechanics, we usually have the unilateral constraint on, and this is a constraint on position level, which you have for colliding bodies, and which leads to collisions. We don't have such an element in electronics, but we have something that I call a unilateral kinematic constraint. It is a constraint on velocity level. This is why I call it kinematic constraint, and it's unilateral because it goes only in one direction. The mechanical unilateral kinematic constraint is a spread clutch, which I always display by such an element, and this works as follows. This element, it can go in, so if you pull on the element, it goes without any resistance. The 2 points move away, but you can't go in the other direction. Yeah, it's a spring clutch, such a thing that you have at the bicycle, at the rear wheel. And the corresponding element in electronics is the diode. So current can only go in that direction, and it's forbidden in the other direction. And here, the forces correspond here to voltages, which can only act in that direction. This was the UPR element. So the second one, the SJ element, is much more important, and I want to go into detail with respect to that element. We know that the SGN means dry friction in mechanics, and it's interesting to observe that it means a spark gap for electrical systems. And this spark gap is important because by using that spark gap, I can design switches. So I want now to explain my switch model. So really, if you want to switch on and off something, there is a SGN function behind it, and I'm not going to explain that. Take here the SGN function. Here we have the current or velocity, and here the forces or voltages. And now you see immediately that this is Coulomb friction, and if you have a mechanical system, then this dA corresponds usually to friction coefficient times the normal force. This is mechanics. Now in electricity, what can I do? Suppose that we have such an element, which is, or suppose we have a spark gap. So here a cathode, and here another one, and here a gap in between, with distance, say, A of t, yes? Now suppose that you have such a branch, which is under load, or suppose you have such an element in a branch, and now start to increase the voltage, the load in this branch, slowly. Then you move at the beginning. If you have no voltage within this branch, then it's clear that you don't have current. So that means you are somewhere here. If you increase now the voltage here in that branch, then you go up, up, until you reach a certain point at which here the breakthrough happens. So that means you have then a spark and current is going to flow. Yes? And this is precisely that point here. And from that point, it's not possible to further increase the voltage, but it will stay at the same level, and the current is increasing. So that means such a spark gap is modeled by such an SJN function. Now I have two possibilities. If I choose dA to be equal to 0, then I end up with such a line as the force element or characteristics. And this means that the voltage drop is equal to 0 and all currents are allowed. So that means what I get is a perfect conductor, or in mechanics, body without friction. The other extreme case is if I take dA to be very, very big, such that I see only that vertical branch of the force characteristic. Then I get in mechanics a perfect constraint, or in electricity, this means that the current is equal to 0 and all voltages are allowed, so that means it's a perfect isolator. As a consequence, switching on and off lights means nothing else than to go from a perfect isolator to a perfect conductor, or vice versa, and switching is performed by assigning the value dA, by assigning for dA different values. For A equal to 0, I get conduction, and for A very big, I get isolation. Yeah? So that means switching is done by changing the values of A. If you now want to invent a switching rule, how to switch on and off, you have to think about the switch operation, and you have now several possibilities. You could either, here we have A of t, you could either slowly switch off a device by a continuous switching function. And you know, if you try to switch off an inductor, then you will get, in the switch, you will get a spark. Yeah, this is known. So if you take such a continuous switching off, you will see a spark, because for mechanics it would mean we slowly increase friction, and if we slowly increase friction, then a moving body will decelerate and will rest, but after a finite interval in time. So we have a non-vanishing time interval until it comes to rest. And this non-vanishing time interval of friction and sliding means a spark in electricity. Another thing would be to switch off discontinuously, so to have one time instant at which we switch off the light. Yeah. There is also a spark, because the inertia needs some time to come to a rest. And if you now try, or if you now want to have a device that can switch instantaneously such that no sparks occur, then you must consider atomic switch operation. So that means you have to put an atom at a certain time to stop the current in the inductor instantaneously. This is the same if you have a moving body. Then the only force that can instantaneously decelerate the body such that it comes to a rest must be an impulsive force. And for the same reason, if you want here that all the sparks are concentrated on one point in time, and to stop the current immediately, you have to take into account switch control, which is atomic. Releasing bodies is done in the same way. So this corresponds to closing switches. If you close it continuously, you have sparks. If you close it discontinuously, you usually don't have sparks, and in general, if you close a switch, there is no need for an atomic switch controller. So I left this out. So the next one, we also have unidirectional switches. A unidirectional switch is just a bidirectional switch for which current can only go in one direction. So from this example, it is already clear that it can be decomposed in a serial connection of a diode and a spark gap. You just have to take the characteristic of the diode and this one of the spark gap, have to add them to get the resulting characteristic of the unidirectional switch. It is more or less the same as for the bidirectional switch, with the only difference that this branch of the SGN is missing. Switching is now performed in the same manner. If you choose the A to be very big, let me say, very big is sufficient, then you have perfect isolation because the whole thing moves up and only this branch is visible. And if you take the A equal to 0, then you end up with a diode. So that means the unidirectional switch is closed. This is the model of a unidirectional switch. So now I'm going to use those models and will discuss it on the DC-DC buck converter. You see it here once again, but here I have introduced two additional inductors. The reason is why I introduced them. It is because I first want to discuss this model because it results in a positive definite mass matrix, and after that I will go to the original model without the two inductors. So this means first extended converter with the two additional inductors, and then I will go to the original converter without those two. The switch control, which is here drawn in blue, is for both models the same. So that means I will start to explain the switch control and then to go to the two different converters. Within the converters, there are two non-smooth elements. This is here a diode, and here a unidirectional switch. And this switch is operated by the values of the A, just as I explained it, by this loop. Now I start with the switch control. It takes here the voltage of the resistance, feeds it back by comparing it with a ramp generator and activates the switch. To get the equations, you see here again the switch control. We have here a ramp generator which gives us a signal UG of D, which can be assumed to be known. Now the comparator, here we have the comparator who does the following. It takes the difference between those two signals, and if the difference is less than 0, then the switch is on, and otherwise it's off. We know now how to operate the switch, because with the A directly enters the unidirectional switch. That means a switch, this is on, corresponds to values of the A equal to 0, and a switch that is off corresponds to values the A equal plus infinity or equal to a very big value. So that means this is switching. Now the comparator voltage is just the difference of those two voltages magnified by a factor k. So if you take this into account, then we can write down the switch control in that form. The A depends on the voltage on the resistor in T, and is equal to 0 if the voltage at the resistors is less than or equal a given function h of t, which is more or less here the ramp function, and plus infinity otherwise. So we have a very nice description of the control of the system. And in my opinion, that way how a control enters the problem here is very important, because I think that non-smooth control is often, very often connected to the values, to adjusting the values of the SGN step function, or to moving up and down unilateral unities. This is a very, very important mechanism for non-smooth control. Yeah? So, okay. Now we have here the switch control, and I go now to the extended converter, which you see here. What I do is the following. This converter consists of 3 fundamental loops. According to those 3 fundamental loops, I use generalized coordinates or generalized charges Q. I denote them like in mechanics, which is Q1, Q2, Q3 with associated generalized currents J1, J2, J3. Generalized voltages are denoted by V, and the branch variables, branch charges, for example here at that element, is denoted by G, branch current by A, and branch voltage by U. Yeah? Now what to do? I use Kirchhoff's current law. That means I take those generalized currents and I express all the currents in the element independent of the generalized currents. Yeah? This is kinematics, which says you more or less that at one node some charges are coming in, and the balance equations of that node gives us that the same amount of charges must left. This is kinematics. Yeah? As soon as I have kinematics, I write down the virtual work with impulsive quantities for the whole system. So by considering each element in the system in that way, yeah, where we have here the virtual work, it's more a virtual action because we allow for impulsive forces. We have here impulsive voltages and virtual branch charges. Now take the kinematics equation, substitute this one into that one, you get this one, which has to vanish for all admissible virtual charges, to extract from this one the equilibrium conditions of the network. Further, take all the branch relations, for example, the constitutive equation for the inductor, or here this one, which is that the voltage drop at the inductor is inductivity times current. Branch current can be expressed by generalized currents due to that equation. Substitute this one into that equation to end up with such a contribution of the inductor to the mass matrix. And here you have the typical WWT vectors that set up your matrices in your systems. So if you do all those steps, you saw that it works quite similar to mechanics. If you perform all those steps, you end up with that equation with a mass matrix, damping matrix, stiffness matrix. Here, the generalized force direction of the diode, voltage of the diode, switch, one part of the voltage of the switch, and here the other part, which I move to the right hand side to display it as an external excitation. Here, local kinematics for the diode and the switch, and here the UPR inclusions. So that means the diode and the switch segmental force loss. If you look at the masses, then we see the following. Here the mass matrix is a diagonal matrix with the inductors. Damping only has one element, which is the resistor. Stiffness matrix is set up by the capacitors, and here you have the generalized force direction of the diode and here of the switch. If you write it down explicitly, then you end up with three equations. This is the voltage equation for the first loop, and here you see all the voltage contributions of SR, of the switch, of the diode, and here of the voltage source. Here is the equation for the second loop, and here for the third loop. And what I now need in addition are those two equations. That means the constitutive equations for the diode, which is an UPR, and which depends here on the charge in that branch, and my constitutive law for the unidirectional switch, which is a UPR that is shifted to positive values by the switch control value dA, as I explained it before. So this is the whole set of equations that we have. And what I want to point out is that this structure is very well known in mechanics. That means there is a certain class of electrical systems with unilateral elements that fits perfectly in with mechanical second order impact inclusion systems. Yeah? And the ways how to obtain the equations are precisely the same as in mechanics, because I derived them here by the principle of virtual work by choosing a minimal generalized coordinates and so on. So everything seems to really work. Now, since we have electromechanical analogy, I can now set up the corresponding mechanical system. For that, I just look at the mass matrix. I see I have 3 entries that are 3 masses with mass A star, L, and LO, corresponding to the 3 inductors. Damping acts only on the third body from the environment, so that means we have a damper here between LO and the environment. Yeah? Stiffness acts between mass 2 and mass 3, so that means we have a spring here. Then this is the diode. The diode works between body 1 and body 2. This is D, so that means we have a spread gauge here. And the switch is 100, so that means the switch works between first body and the environment. And what here the people from electronics do is they take this UR, feed it back, and operate the switch. The UR here is the voltage in the resistor, which means it is nothing else than the force in the damper here. They feed it back and operate the switch by maybe impulsive force values. So this is the corresponding mechanical model. Now Now please look at the 2 additional inductors that I introduced. To go to the original converter, I have to set L star and LO equal to 0. And now please look what happens with the mass matrix. If I take L star and LO equal to 0, then I get a degenerated mass matrix. Yeah. There are 2 less masses in the system. Even more, please look at the first row of my system. I would have here a 0 in the mass matrix, nothing in the damping matrix, and nothing in the stiffness matrix. So that means this system is absolutely underdetermined. You can't use any implicit integration algorithm to treat that system. It is definitely impossible, because it's too degenerated. Nothing is there. Neither a mass, nor a dampness, nor a stiffness. Nothing. So to draw the picture of that system, we end up with that one. You see, I just took this inductor equal to 0, and here this also. So that means that switch and the diode, they come together to form one very strange element. The resulting thing is here. Here you have the original buck converter, and here the corresponding mechanical system. And now what we see is the following. We have here still the 3 loops. The second loop contains inertia. So that means this is a dynamic loop. The third one contains a damping spring element. So that means the third one is a purely viscoelastic loop. And the first loop is very strange. We don't have even stiffnesses, but we just have spread gauges at which some certain forces act. And this is the difficulty and the peculiarity of that system. Now I try to solve that system. For that, I take the original equation that I showed you before. Yeah. Loop 1, loop 2, loop 3 with the inductors set to 0. Then the 2 force element and my switch control. And now I change over to new variables, and I take the branch current IL. This is that one. And branch charges GC. That are the charges here in the capacitor. So I have chosen those 2 variables because people from electricity do the same. And if you do all the transformation, then you end up with that set of equations, which is reasonable. Mechanically, if you interpret the new state variables, you take here the position of the mass and here the relative position of the spring, and that's it. However, we have still 3 equations according to the 3 loops, and we have the problem that 2 of that unilateral UPR constraints come together here. So what I try now is to, and this is also the reason that I have still an additional variable here, which is IS. This means the current here in the switch. Now the problem is how to get rid of that first loop. And what I'm trying to do is to solve the first loop. That means to eliminate here the IS, yes, which is the current in the switch or the velocity here of that element, that strange massless element here. For that, I take the voltage balance of the first loop together with the two self-valued constitutive equations. And what I do now is the following. First, I take this one to eliminate US from here to end up with those two equations. You see here some voltages, and here on the right hand side, here IS, and here IS within the UPR, and this is what I want to remove from the set of equations. So how to do this? I take both equations, invert them to have a UPR minus 1, take into account this one, and then I get two equations, IL, IS, and here the UPRs. So those two inclusions tell me that I have, now by eliminating the IS, I have to add the two UPRs, which gives me that expression. And now it depends on how the UPRs are arranged relative to each other. So for example, this one is the blue one, and the other one, the red one, is shifted by a certain value. And now it depends whether this value is greater or less than 0, because I would add up these two situations. It's either it's located here or on the other side. So by adding those two UPRs, what I obtain is a new UPR, this one. But now depending on which side, I have to take, if it is this configuration, then the resulting thing is that one. And if the red one is due to the negativity of that expression on that side, then I would end up with a blue one. So that means the result is a UPR shifted by values dp, and this dp is obtained from a max condition. It's either 0 or that other, it's the maximum value of 0 and that one. I solve it back for du and dp to obtain this one, abbreviate this by ds to end up with a pure UPR, for which that value dp is determined by this max condition. My new equations are loop 2, loop 3. Now, loop 1 has been used to solve the UPR inclusions. I got from both UPR inclusions the new UPR, which acts on ds, the max condition, and here is my switch control. Now I can, in addition, solve the max condition, because I just have to check the two cases that GC, either if it is less than this one or bigger than that one, to evaluate it. I get the two results. If GC is less than this one, then my EA is equal to 0. So that means this one consists only of UO ET to take the maximum value is UO, because this is a positive constant. So that means, as a result, I see that my switch control is non-atomic in any case. And for the second case, I'll take this one. Take this two, substitute it back into that equation, and end up with a minimal form of the converter. So that means this is really now the whole converter equations in a minimal description. You cannot further reduce that set of equations. You see here again, this is the description of the whole inverter. And what happened is that we solved the first loop to just have one input signal, which is controlled by the values of UR. And those two things come together to one unilateral constraint. Here you have some calculations which agree with those done by Gerard Olivier. Vice versa? Olivier Gerard? No.
Gerard Oliver.
Oliver, right. We took that DC-DC buck converter because it is used in the literature and it's discussed a lot. So we had computational results available, and what we did is we now applied a time stepping, an implicit time stepping scheme, an adapted time stepping scheme to those equations to end up with precisely the same results that we found in the literature. So what the people there did is they did some ad hoc or intuitive evaluation of all the inequalities and ended up with the same results. The interesting thing is that we can arrive with precisely the same equations by doing a very, very rigorous analysis with Z-valued force laws to condense really the equations to a maximally constant system and to evaluate them. It. Another interesting point that I want to mention at the end is the following. We have still some maybe impulsive switch control DS here, which results from that unilateral constraint. This one is only needed for initialization of the system. If the system is at the beginning initialized in a wrong manner, so that means if you take an initial condition such that this mass is moving to the wrong side, then one impulsive switch control is needed to stop it, which corresponds to a completely inelastic impact, and which is done here by the impulsive switch control. But once the system is in proper operation, you don't need any impulsive switch control here, because this is a system that cannot generate just from mechanical intuition, that cannot generate any impulsive behavior from itself. Only exception if you choose here a very bad switch control which corresponds to Pareto problem, which is still possible in electrical networks because they can do such things. Okay, that's it. Thank you.
Maybe we have time for one short question.
The answer to that. So I have a question. You were saying that as L star goes to 0, you actually get something which is glucose, but shouldn't you recover somehow the equations for the wire, for the situation when you have no element there?
It depends.
Okay.
It's a question of modeling.
Okay.
So what we did is we have chosen precisely the model that the people from electricity use. And if I do then a strong analysis, a rigorous analysis, then it turns out to end up this way. However, there is a second approach called the flux approach, where everything works quite the same way around. Yeah? In the flux approach, you take as variables the voltages, and here in the flux approach, voltages correspond to kinematics and currents to forces. And here everything works quite in the other direction. It's a dual approach. And if you model the buck converter with the flux approach, then everything works. Because then capacitors have to be looked as if they would be inductors and so on, and then it's not too degenerated. Then you can solve it.
Okay, so one more question.
Your analysis, you are studying this example of DC buck converter, DC buck converter. But this is too specific. Suppose somebody gives you a power converter, electrical circuit, including some switches. Is there a methodology to find
This is a methodology, yeah.
It
is a full methodology because I showed you the virtual map approach. And based on the virtual action approach, let me say, you can formulate the whole system, include your inequalities, and then it works like a machine.
Yeah, okay, but you added some inductors, right? How can I know where should I add the inductors?
No, it's not. It's not necessary to add the inductors.
Why did we do that?
Why? Because I wanted to show you that there is a special subclass of mechanical networks that correspond with mechanical systems. This was the reason. And to have a basis to do my reduction steps analytically.
So you claim that any electric circuit with switching elements you can drive a model in a specific way.
Should be possible. Yeah.
Really quick question. So is there an analogy to non-inelastic impact? So the diode model is inelastic impacts, right?
No.
But that's not quite true.
Impacts in electrical systems are very, very, very special. Very special. I mean, the only source, in my opinion, how to generate an impact, so that means a velocity jump together with impulsive forces. Yeah? The only way is it to do it by atomic switch control. Because a brake clutch cannot produce impacts by itself.
There's no mass.
A spread clutch, no, even
No,
if
not
it,
by itself, but if
it
has
can
other-
react on the impacts, of course.
Right.
But it cannot produce an impact like in a mechanical system with a collision, because it's formulated on velocity level. That's the point.
Right. But you did have impulsive forces.
I did not include that. I did not exclude them, although I knew already that there were no impulsive forces. But think about the initialization step when you formulate your initial conditions. If the system is inconsistent, then you have to do something, yeah,
Right.
to correct it, to
And-
reach a feasible state.
and-
And this reaching a feasible state corresponds precisely to an impact behavior.
To inelastic impact.
Inelastic impact, yeah. I've chosen inelastic because I really can't imagine that all the charges bounce.
Well, but I mean,
Yeah.
we don't know.
We don't know,
Yeah.
but it's not a problem to add anything else.
Okay, so thank you again, Christoph. Next talk is by Hans.